We'll wait to vote on the test just in case it's split, since there's 4 of you. Once we get 5, then I know it'll go one way or the other. This is 10.5, area and arc length in polar coordinates. And the arc length we won't spend much time on. I wasn't planning on spending much time on it, and then I read it's optional before class. In order to work an arc length problem, you have to design it to be pretty easy, or use technology. So, now here's our theorem: the area in polar coordinates. If f is continuous and non-negative on the interval, alpha to beta, including those values, and beta minus alpha is between 0, not including 0, and less than or equal to 2 pi, then the area of the region bounded by the graph of r equals f of theta between the radial lines, theta is equal to alpha, theta is equal to beta, is a is equal to 1/2 times the integral from alpha to beta of f of theta squared d theta, or 1/2 the integral of alpha to beta of r squared d theta. Now here's our power reducing formulas. Sine squared is equal to 1 minus cosine 2u over 2. And cosine squared of u is equal to 1 plus cosine 2u over 2. And tangent squared is equal to 1 minus cosine 2u over 1 plus cosine 2u.
That's just another way of writing it.
Yes. Because you'll have a lot of problems that end up with sine squared and cosine squared. I'm not sure if I've seen one end up with tangent squared. But I pulled this from another page, just the power reducing formulas. So I expect the problem would be so hard if you use the tangent squared, you wouldn't be able to solve it. If you use this formula. There's another way to find the interval for tangent squared, of course. Now these first problems, it says write an integral that represents the area of the shaded region of the figure. Do not evaluate the integral. Though I know, interesting enough, I think CalcChat does evaluate it, but we'll just do the setup.
What section is this?
10.5.
Wait, this was no 10.5.
We never got to 10.5. Yeah, we spent a lot of time on 10.4 last time. Okay. Now, if you look at right here, our formula is a is equal to 1/2. Then the integral, going off this formula right here, and then you have your bounds, and then you have your function squared. So we'll have our function squared and d theta. The hard part really on this, I mean, the 1/2 is pretty mindless, and squaring this is pretty mindless. The one thing that's hard is figuring out these bounds. Now, if we looked at this point right here, what would you probably assume the angle is? The one I put right here. 0? Yeah. If I were to put 0 up here, sine of 0 is equal to 0. It's equal to 0. So then 4 times 0 is 0, radius being 0. Okay, so you could buy that, couldn't you? Now this one up here, the assumption would be that it's pi over 2. Well, let's think that through. If I were to take that and plug that in here, r is equal to 4 sine of pi over 2. Sine of pi over 2 is 1. That'd give me a radius of 4. Well, if that was my angle, does that look like I went up a radius of 4 to put the point here? It does, doesn't it? Remember, when we're dealing with polar here, we're dealing a series of points all along this. And there's a radius associated with each one of those points. So yeah, this one's pretty straightforward. It's 0 to pi over 2. Now I do a lot of setup on these, but I probably won't go through and actually do the problem complete because they're all the same, or it seems like they are anyway. Let me go ahead and finish this one. Okay, if I square this, I got 4 squared and sine squared. So 4 squared is 16. I can take it out in front of the integral. So that's sine squared. Again, our sine squared is equal to this. So 1/2 times 16 is 8. 0 to pi over 2 of 1 minus cosine 2 theta over 2 d theta. Going to split that up. 0 to pi over 2. And that 2 down below I can bring out in front is 1/2. So we got 1 minus cosine 2 theta d theta. 8 times 1/2 is 4. And 0 to pi over 2 of 1 d theta minus 0 to pi over 2 of cosine 2 theta d theta. Well, this would be theta from 0 to pi over 2 minus, now this would be a u substitution. I think u equal to the 2 theta. D would be 2 d theta, so I need a 2 inside, so I put a 1/2 out in front. And the integral of cosine is sine 0 to pi over 2. This becomes pi over 2 here minus 1/2. And then I plug that in. I'm going to have sine of 2 times pi over 2 minus sine 2 times 0. Twos cancel. I got sine of pi. Sine of pi is 0. 2 times 0 is 0. Sine of 0 is 0. So all that drops away. It's just a big 0 there. Which, assuming I did right, I get 2 pi. I guess that's right, isn't it? This is a circle. of radius 2. Area of a circle is pi r squared. So if I put in a radius of 2, 2 squared is 4 times pi is 4 pi. Half of the circle would be 2 pi. Questions on that?
Did we calculate all that, or could we just do that?
Oh, for that one?
Yeah.
If I didn't specify otherwise, yeah, you just write down 4 pi. You wouldn't do it, or not 4 pi, 2 pi. You wouldn't do it work. Okay. I don't know. I can look it up later on. I use the same one I created 8 years ago. So let's see. Is there anything? Yeah, this one's a good one. Let's take a look at this one. Then I'll just do the setup on this one. Some of these you can just look at and see the setup. Others are harder. Now, what would be your guess on the beginning angle and then the closing angle? Assuming this was our starting place and this was our ending place. Well, assuming this is our polar axis where we start, coming up to here, that angle would be pi over 2. And if I started my polar and went all the way down to here, that would be 3 pi over 2. And then 3 minus 2 sine theta squared d theta. Now, I'm going to show you how to check that. Now, that's what we assume by looking at it. And we're going to use the trace feature on our TA3, TA4 quite a bit on this. Because sometimes it's just hard to see how it goes. Sometimes the way the loopy-the-loop goes is just not what you'd guess. And you could build a big T-chart to see the pattern, but it's a lot easier to use your trace feature. Okay, so we're posing that it starts at pi over 2. I butchered it. Okay, so if I look at pi over 2, if I plug that back in my original problem, r is equal to 3 minus 2 sine of pi over 2. 3 minus 2 sine pi over 2 is 1. 2 times 1 is 2. 3 minus 2 gives us 1. For my starting place, does that seem like a radius is 1? It does, doesn't it? So that checks. If I went to my ending and plugged in 3 pi over 2 in for theta, I get r is equal to 3 minus 2 sine 3 pi over 2, which gives us 3 minus 2 times sine of 3 pi over 2 is negative 1. Negative 2 times negative 1 is a positive 2 plus 3 is 5. Does that seem like it's a directed distance of 5? It does, doesn't it? Because coming down here, that's obvious. And then from my origin, coming 5 units would take me right here. So that does check. So that is our setup on that. Now these next problems are just simply asking you to find the area of the region. And some of these don't work. I especially want to show like a problem like number 13 or 15 or something like that. These are just using power reducing. I probably want to show number 9 too. That's very unique. Let's take a look at number 7. Oh, you've seen one like it already. Interior of R is equal to 6 sine theta. Okay, if I come here and put in 6 sine theta. Oh, press your mode button. And where it says function, par, pole, seq, you want to choose pole for polar. And then when you go to the y equals, you should see your R1. Remember, zoom and z standard seemed like gave us the best last time. Now, understanding the nature of these graphs helps you in some of the setup, so you don't have to. You can just do like half the work type of deal. Some cases it's doesn't hurt to do all of it. 6 sine theta. Did you do zoom 6? The other thing I think has to be true, I'm not sure, but always make sure I'm in radians. Because that's what polar is built around, is radians. You never see degrees. Okay, so it works in radians. I don't know about degrees. Oh, does it? Okay, that doesn't matter then.
Radiance makes it into a bajillion stars.
I don't know. Must be a flaw with your calculator. I expect it's a flaw with that particular operating system. You have radians that. That's weird that Radiant screws it up on that. But these had different operating systems, so I don't know. You might think, well, they all have the same, but if you did I think it's second plus. Yeah, second plus takes into the memory. And the first one is the about. And see, my operating system is 2.55 MP math print, I think is what that stands for. Some of you, maybe all of you, will have different numbers there. Yeah, 4. That's an old emulator. Yeah, so 2.43. Well, that's older than mine. See, but you just bought yours. See, that's what you can't make any kind of sense about it because the operating system, they build these, they put them on, shelves for periods of time, and it may be 2 years before you buy it that it's been sitting there. Yes, there is. Yeah, I haven't ever done it. But the students have told me they've done it. Yeah. That's what students have told me. I never have done it. So I figured that when the moment I'd do it, I'd screw it up. But you really can't screw it up. If you did that, if you just did a factory reset, if you did a second plus, and you go back to the reset here and you reset everything, it'll put it back to the operating system is loaded when it was first came out of the factory. Oh, is there for resetting? Yeah, I have some people come in college algebra, their y equals look so bizarre compared to everybody else's in the class. I just haven't reset it right from the very beginning. Somehow, it gets a newer one loaded when it comes out of the factory, and then resetting it sets it back to the one that was loaded when it was first created. How interesting. Is your just out of curiosity, is your connected on or dot under mode? Yeah. See, that's the only thing I'd think of, but I don't know. Okay. Now this one, CalcChat, if I remember right, because I was checking these all as I went along. CalcChat goes from 0 to pi. It's a full circle, yeah. Because starting at, let's see. If I started down here, well, to begin with, my angle's 0, right? Because I haven't started going around it. Because again, remember, we're like having a bunch of lines going through as the angle increases. Those lines are directed distance, are r. So initially that's equal to 0. And if I were to plug 0 in there, sine of 0 is 0 times 6 is 0. So r is equal to 0. So that makes sense. As I keep moving this angle further and further over, clear over to the far here is not 2 pi, it's pi. And if I were to put pi in there, we'd have sine of pi, which is 0, times 6 is 0, r is back equal to 0. And that works. If you did that, r is equal to 1/2 from 0 to pi of your function squared, d theta. That'll give you the answer. Another way you could do it, which will give you the exact same answer, is instead of going, and I don't think this is probably necessarily any easier in this particular example, but instead of going clear to pi, if you look at the right side here, is for a circle, is that symmetric to this side? It is, isn't it? So I could go from 0 to pi over 2, which will give me half the circle, and then multiply it by 2. Uh-huh.
For this specific problem, it's asking for the entire circle?
Yes. Because this asks for the interior, which is everything. Right, the other one is half one.
But why are we now doing pi? Because no.
Now, if we thought it was a circle, our actual radius, not a directed distance, but our radius would be 3, wouldn't it? And area is equal to pi r squared. Put r in there 3, you got 3 squared, which is 9, gives us 9 pi. I don't know what that is exactly. It's probably 27 or 28. What? I'm not. I'm just looking at it as being a circle. It'd have a radius of 3. Now this I don't know. I'm not sure if I ever tried this, to be honest. Okay, I got that. Let's see if the integration works on it. Let's see if we can do a second trace to see if it's there. No, it isn't there. What? Yeah. Yeah, because eventually it gets to the maximum, which is does get to the maximum. How do you get the radius?
How do I find the radius? I click trace and click the right button.
It worked on that one. Might not work on all of them necessarily. Yeah, if it's shifted a little bit, then it wouldn't work. But I was pointing, I didn't think it gave you R direct. It would give you, if you went up here, it always give you the diameter, right? Which half of that would be radius. Okay. What do you think would happen here if I did this, 0 to 2 pi? Twice? Yeah, it'd be twice. So if I come over here, and let me change back. I don't think that mode actually matters in terms of the integration, but I could be wrong. Let's go back to function. And I'm going to put in my initial problem. Now, that 1/2 is out in front. I can move that 1/2 inside. So 1 divided by 2, beginning parentheses 6, sine x, closing parentheses on that, squared. Second trace, choose number 7, and 0 to pi. Yes. 0 to pi. That does look like 9 pi, doesn't it? As I said, 9 pi is like 9 times 3 point something. So 2728. So that gave us that answer. Now let's instead look at 0 to 2 pi. So 0 and 2 pi. Notice how we get double the result. This is why it's important for you to understand these limits of integration here. That's really the hard part on these. You could use your calculator and get that, but if you don't set up the limits of integration right, it's just going to give you the wrong result. That's why it's handy to say, well, I'll just do 0 to 2 pi in every problem. Well, yeah, you could, but then you'll miss 80% of them. There's a squared on the second line there. Correct. This is a good way to check your integration. If you were doing it by hand, like on the test, I ask you to do it by hand and find out the actual area. If you just flip over to the function mode, put in the function and put your limits of integration in there, you can check it to see if you got the right answer. So you know you got that answer correct. Okay, I'm gonna go back to polar. Doesn't work on the other one? You just bought that one, didn't you? Still should have, those things hardly ever go. The only thing that really goes bad on is the screen, seems like. Yeah, resetting them may be like you indicated. Yeah, because when it starts doing weird things and okay, number 9. And we'll actually work number 9 out to show it all the way through. Yeah, radiance is when you're dealing with these radiance is usually the one you want to be in. But then again, I don't remember. I always just make sure it's in radiance. I don't think the last time I tried degrees. Okay, 1 petal of r is equal to 2 cosine of 3 theta. If I remember right, this one's weird. Okay, go to y equals clear 2 cosine 3 theta. And then press graph. You probably can't see it. So zooming is what you'd want to do. You do zoom, choose zoom in, and it's waiting for you to zoom in where you want to put the zoom in at. So it's waiting for you to position your cursor so you can use your arrow keys, but we want to write an origin anyway. We'll press enter and gives you that. If you notice that while I was graphing, it did something weird. Okay. 1 petal. Okay, so we just want 1 petal. If I press my trace, notice where my cursor is. It's over here at the far right. It's not here in the origin. And if I start pushing my right arrow key, that appears to get it over to half the leaf. And you might think, well, I just continue pushing it and have it go all the way around the leaf. But if I start pushing the right arrow key, notice what it does. It's down here, isn't it? So it doesn't circle around like go here and then back to here. Yeah, it does that. So that's why it's important to understand that pattern on there. But I know that I can take from 0 to whatever this value is. And earlier I didn't keep it, but I went into Excel and I created a bunch of pies to get all the different values. I should have saved it. Pi over 2, pi over 3, pi over 4. I don't think you have to go very far. What did hard code 2 in there for? Okay, B1. Okay, so the value that we see on our trace here is 0.52, so forth, which is pi over 6, isn't it? So this (0, 6), and we got the 1/2 out in front here, an area. Now 0 to pi over 6 is going to give us half a leaf, won't it? So to get the full leaf, we need to do what? Multiply by 2. Yeah. So multiply that by 2. Squared d theta. Okay, so 2 times 1/2 going to cancel, and 2 squared here is 4, so I can bring that out in front. And this would be cosine squared 3 theta. Now, it's second formula here, and u is whatever follows your cosine squared. So on this one, u would be 3 theta. That has nothing to do with taking the integral. That has to do with just the formula. And our formula then says, cosine squared is 1 plus cosine 2u. So 1 plus cosine 2 times u, which is 3 theta, over 2 d theta. Now this 2 down below, I can move it out in front as a half. So 4 times a half. 0 to pi over 6. 1 plus cosine 6 theta, d theta. Hopefully I don't screw this up. 4 times a half is 2. The integral of 1 is theta. This would be a u substitution. U is equal to 6 theta. Du would be 6 d theta. So I need a 6 inside, so I need a 1/6 out in front. And the integral of cosine is sine. From 0 to pi over 6. Okay, so I'll plug in pi over 6. So I got pi over 6 plus 1/6 sine of 6 times pi over 6 minus, plug 0 in. I got 0 plus 1/6 sine of 6 times 0. These 6's would cancel. I got sine of pi, which is 0, times 1/6 is 0, so that drops away. That 0 drops away. 6 times 0 is 0. Sine of 0 is 0, times 1/6 is 0, so that drops away. So let's, assuming I didn't screw it up, is pi over 3. For some reason, I have a lot of trouble with the numbers on these. I'll put an extra half in there, or I'll drop a half, and so forth. So if you do that on a test, I'm very forgiving in terms of grading. Just because you'd be shocked at how many of these I did a lot of the steps in my head and I'd screw them up. I'm not as sharp as I think. If you're like me, you're not as sharp as you think, then you need to write out all the steps. You make less mistakes. So.
How did you find 5 or 6 again?
Let's see. I started here. If you notice where my flashing cursor, I'm in trace. You notice where my flashing cursor is. That's theta is equal to 0. And it tells you at the lower left-hand corner. And then if I start moving my right arrow key, I keep moving it until I get half the leaf. Oh. And by the way, the fact that it just looks like it's there, that isn't really good enough. What tells me technology-wise is see what the y value is equal to? Negative 5.1 e negative 12. That means you move your decimal place 12 places left. And that's 0. It's not exactly 0, but it's close enough for most purposes. Yes, I went over in Excel and I used an Excel function equals pi divided by a cell, and I filled it down. So yeah, this would probably be a handy thing to have come test time. So you're sitting there fumbling around. What's pi divided by 6? What's pi divided by 3? What's pi divided by 4? You have this right here, and then when you use the technology, it tells you exactly which one it is. I don't think you need to go above pi over 16. I'd be shocked if there's anything like that. Most of them are like up to pi over 8. I would save you time and test time. Because like I say, the setup is really the challenging part on these. Okay, that was one pedal. Number 11. I think that has a ton of pedals. So let's look at number 11. So that took me playing to get to the number of pedals I wanted. R is equal to sine 8 theta. And want 2 pedals. So I got sine 8 theta. And if I press graph, I think there's a total of 16 pedals there. If I remember right from last time, if we had an even number before our theta, then we had twice as many pedals. Obviously, I'm going to have a hard time tracing that and seeing anything, aren't I? So what you need to do is you need to go to the window and start reducing this. 6.2831 is 2 pi. So I want to put pi in there. And then press graph. And we see our number of pedals is reduced. It looks like 8, I think. Still want to reduce it more or less than that. So I'm going to go to my window. Instead of pi, I'll put in pi over 2. And press graph. Closer now. But really, if I'm going to look at two pedals, I'd like just to have 1 pedal. And then multiply it by 2 to have 2 pedals. So let's keep reducing it. What was that? That's pi over 2, so pi over 4. What tells you? Yeah. And so if I take it down 1 more, looks like I get 1 pedal. So instead of pi over 4, I'm going to come over here and put pi over 8. Now I can't see it very well, but that's fine. Because I can do a zoom, do a Z box. Remember our Z box? Choose it, and then you do your up arrow key, left arrow key. You want to put it in the upper left-hand corner where you want your box to be. And then you press enter 1 time. Down arrow, right arrow. And over there, press enter. And there's our pedal. Now I can do a trace to see if it's actually going to go around that. If I did my right arrow key, you see it's going exactly around that pedal, isn't it? So it's not bouncing around to another pedal on the other side. So that's good. Because that means that we can use that entire interval to help us figure it out. Now, this takes me to 0.3926. Pi over 8. So I'll do that one. It is. You'll see a pattern on some of these. It helps you once it clicks with you. Okay, and then sine of 8 theta squared d theta. Now this is giving us one petal, so what would I have to multiply by? What?
Oh, 16.
No, we want 2 petals.
Oh,
Multiply by 2, right? If I change the problem, said I want 5 petals, just multiply by 5, so forth. Now, this is what we believed for the calculator. And you could rely on the approximation you'd see for the values when you're tracing it. But if you actually plugged them in, let's see what it gives us. Assuming it's circling around that petal, which we verified it was. If it's not circling around just that petal, then this theory doesn't work. If I plug that in, I get sine of 8 times 0. 8 times 0 is 0, sine of 0 is 0. Okay, that makes sense. It's starting out at the origin, at the pole. They call it for polar. And if I plugged in pi over 8, the 8s would cancel, and I got sine of pi, which is 0. So it's back to the origin. Now, I went through kind of the long process on that. If you had a different problem, like you had this. Assuming, once we narrowed it down, that it traced appropriately, what do you think my limits of integration would be here? Yeah, because this is pi over 8, and it was 8 theta, wasn't it? So pi over 20. Yeah, because we're just trying to get one leaf. Now let's see if that actually gives us one leaf on here. As that'd be such a nightmare. You could no more try to decipher it than fly to the moon. If I did a zoom 6, you zoom in. No way you could tell anything about it. Nice snowflake. But if I went to my window and changed that from 0 to pi over 20, and then my graph, do a zoom box. Still doesn't see very much. Let me do a trace. And there. I might have lied. It's not taking us back to the beginning, is it? It should. If I didn't do my window setting right. Oh, pi over 20. What do I keep doing? Pi over 20. That's what I had. I don't know why it doesn't work. I mean, I can plug in the values and see it should. It's like, but the technology fails. I suppose, like you say, there's some kind of margin of error, or something that's causing it not to work. Or maybe it bounces to another part of the graph. I bet it bounces to another part of the graph. See, this is where I'd probably have to build a T-chart, unfortunately, to see what exactly it's doing. Oh well. Do you want to see how to reset it? Just do a second plus. Go down to reset. All change it to all. Just go to the right, and go to all, and then all memory. Yeah. Yeah. If it can be fixed, that'll fix it. Did it look good now? I should have mentioned you just lost your games. Where are the games at? Apps? Yeah. Well, it comes default with some. And it wipes them out when you do a reset like that. I don't know about the one in the back. Think so? Yeah, I downloaded Tetris to my TI3, TI4. I had a lot of fun with that when people were taking tests. I'd sit there and play Tetris for an hour. And then I had to reset my calculator and lost Tetris. I've been too lazy to go out and download it again. Does everybody know where the websites are to download programs? Yeah. No, there's a big one out there. Let me see if I can remember. Or Google it, I should say. Program download. It's ticalc.org. And then when you go there, you can choose like different. If I went to calculus, there's programs to do limits, about everything you can imagine. Newton's approximation, arc length of a curve. That's what we're getting ready to do. Bessel, yeah. Calculus 1 and 2 packs. So I guess there's a ton of things you can download. Yeah, I tried to get TA3, TA4 banned from college algebra at Cali. The other instructors thought I was insane, but I know what the calculator can do. And you can download everything you need to do in college algebra. There's a program in here you could download for it. So if you're clever technology-wise, you can download it. It'll do the work for you. And some of them are so good they'll even show the steps. So it's like, well, you need to show your steps. It's like, well, okay. And I demonstrated a quadratic formula program that shows all the steps too. It was a beautiful program. And but I said, oh, that'll make it too hard for Johnny. They can't pass college algebra. Okay. Now we'll do the next section too. Let's see. You're right. Time slipping away. I'll just do setups on these. Let's look at 13. The setup on that. Although really these are kind of all the same. Figure out the angles that what you're trying to find. Now, when they're referring to the polar axis, that's the polar. Yeah, the horizontal. Yeah, exactly. Kind of your starting place when you start rotating around. 0 degrees or 0 radians. Interestingly enough, the polar axis goes all the way across, so it's just not the right-hand side. Possibly. But if you do a zoom 6, it'll set it back to your standard. It'd be a weird problem that'd go beyond 2 pi. So I don't think it can go up past 2 pi. Is that a true statement? I don't think I've ever seen one go past 2 pi because 2 pi is all the way around. Okay, so I want what's on the bottom there. Oh, is it still not working? Crooks. How much did they rip you out for that? See, I just couldn't sleep at night if I ripped somebody off. You know, I'd rather lose $20 and sleep well at night than think I just ripped somebody off. I don't understand people who do that. Okay. I'll press trace. Now I'm right here, and if I do a right arrow key, you see the progression of this is going across. We're not even to where we want yet. I get to here, and look what our theta is. 3.14159. I know what that is. That's pi. So it appears like I'm going to start at pi. Now, if I keep doing my right arrow key,
Where did you start at? What was your possible start at?
oh, I kept doing the right arrow key until I got to this point right here. Because we want what's underneath it. Now, I could stop right here. That would be half of the area I wanted to find. Look up what that decimal is. But if I keep on going, there's nothing saying you have to stop there. If I keep going, it goes to 6.28, which is 2 pi. And then 6 plus 5 sine theta squared d theta. And then you work the problem from there. Now, to me, the setup's a really interesting part. On the test, I'm not going to torture you requiring to do it by hand. If you want to go then flip over to your function mode, just plug this in, get the decimal approximation. I'm fine with that. So, let's see. Now here's some formulas from trig. It's where you're adding and subtracting sum and difference, two angles. Those come in handy. Now the next problems, and I may just work one example of this because this is an optional topic. I just found it kind of neat. I'm not sure where you'd actually even use it at, but I liked it. Finding points of intersection. And I'll upload this PowerPoint. Like this, these two graphs here, you're trying to find these points of intersection. So let's look at number 27. No. Okay, find the points of intersection of those. And we can see they look like there's 3 of them. Step 1. First solve each equation for r, then set each one equal to each other and solve. So these are already set, both set equal to r. So I can set them equal to each other. 1 plus cosine theta is equal to 1 minus cosine theta. Take that 1 over there, 1 minus 1. Take the let's do that different. Not that it matters. If I take negative cosine theta over there, it becomes a positive cosine theta. Take the 1 over there, and I get 1 minus 1. So I get 2 cosine theta is equal to 0. Divide both sides by 2. We get cosine theta is equal to 0. And if I think where cosine is equal to 0 at, I'm going around my unit circle. Cosine is our x. That'd be pi over 2. And that would be 3 pi over 2. Now this, I can actually, and the reason why I'm showing this, not just because it's kind of neat, but you go out and you need to use this in real life. I've mentioned before they'll give you some kind of software package for it, right? But software package may not be smart enough to tell what your limits of integration should be. So you may have to do this preliminary stuff before you plug it in and have the calculator just gives you the answer. Okay. Step 2. Then plug negative r into r and theta plus pi for theta, and solve using the same technique as step 1. And I left something off there. Into the first equation. You don't do it in both equations. We saw that last time. Remember where we have our point down there at one quadrant, and then we would add pi onto it or subtract pi and flip the r, so it'd be over in the other, and then it'd flip back and go back. So that's just another way of representing it. So if I do that to my first equation, this becomes negative r is equal to 1 plus cosine of, and then we plug in theta plus pi. My second equation remains as is. Now I'm going to multiply the first equation by negative 1. And that's going to give us r is equal to negative 1 minus cosine theta plus pi. And this one is r is equal to 1 minus cosine theta. Now, since they're both equal to r at this point, I can equate these two. So I got negative 1 minus cosine theta plus pi is equal to 1 minus cosine theta. Now, cosine of theta plus pi, that's where I'd use this formula here, where I got 2 added together. So based upon this formula, the first one's alpha, the second one's beta. So this is alpha, and this is beta. And from my formula, I'm going to have cosine alpha, cosine beta. So cosine alpha, cosine beta, minus sine alpha. What if I put beta there? That should be a pi. Sine beta, which is pi, equals 1 minus cosine theta. Now cosine of pi is, what is that, negative 1? So negative 1 times cosine theta is negative cosine theta. Sine of pi is 0. 0 times sine theta gives you 0, so that drops away. 1 minus cosine theta Negative 1 plus cosine theta is equal to 1 minus cosine theta. Take the cosine thetas over to the left side. And we got cosine theta plus cosine theta is equal to, take that negative 1 over, 1 plus 1. So I got 2 cosine theta is equal to 2. Divide both sides by 2, and I get cosine theta is equal to 1. And cosine theta is equal to 1 at 0. Now the last technique we have to use to find theta, check see if they both pass through the pole, which is the origin, by plugging 0 in for r and solving. If there's an answer for both, then they both pass through the pole. So I'm going to go to my equations. 1 plus cosine theta, 1 minus cosine theta. It's at r equals 0. So 1 plus cosine theta is equal to 0. 1 minus cosine theta is equal to 0. So take that over, gives me negative 1. This one take negative cosine theta over. Let's see, that's equal to negative 1 at pi. And this one is 0. So both of them have an answer, don't they? Which means that the pole is one of our choices. Which is not a big surprise when you look at the graph, right? Does it look like it passed through the origin? Yeah. And we already actually have that answer. Because when we start plugging these in, if it passes through the origin, what's my radius going to be? Or what's your directed distance, r, going to be? 0. And so if I plug these in, I'm going to get r is equal to 0. Probably this last one if I had to guess. What were my functions? R equals 1 plus cosine theta. It doesn't matter which one you plug it into. I'm going to plug it in this one. So r is equal to 1 plus cosine of 0. I guess I'm lying. This cosine of 0 is 0, or 1. 1 plus 1 is 2. Let's see this one. R is equal to 1 plus cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0. 1 plus 0 is 1. 1 plus cosine pi over 2, which is 0. So r is equal to 1. I guess we don't got 0, do we? Okay, so if I start with r is equal to 0, all right, I already found that up here. Never mind. Then these would be our angles for the respective ones. Anyway, that's how you find your points of intersection. Now here's your formula for the arc length. And let me just set up one problem. I'll set up 55. Easy problems. You might actually want these on a test. No, no, this is arc length. Okay. To find the arc length of a polar curve, you need alpha and beta, and that's always given to you right here. So you don't have to do any kind of tracing or anything. That's always given. This is alpha. This is beta. Besides that, you need your f of theta. That's always your r. So f of theta is equal to 4 sine theta. The other thing you need is you need your derivative, f prime. Derivative of sine is cosine. And that's everything we need for our problem. So then, 0 to pi, that's your alpha to beta, square root of your function squared, so 4 sine theta squared, plus your derivative squared, so 4 cosine theta squared, d theta. Now I'll go ahead and finish this one since it's so easy. Square that gives me 16 sine squared plus 16 cosine squared, d theta. I can factor a 16 out, and that gives me a 4 out of the radical, so I can put a 4 out in front. And then I'm left with sine squared plus cosine squared inside, which gives me 1. And square root of 1 is 1. Then the integral of 1 is theta from 0 to pi, which would give me 4 pi as my answer. These you cannot solve unless they're designed to be easy. Because when you get anything more complex, there's just no way to solve it without some kind of numerical method.
Yeah, you took that thing where sine per second, cosine per second.
Right. Yeah, Pythagorean theorem. Yeah. Now, it might seem like, well, yeah, that's it's nice, but how many of these are really designed to be that way? A large amount of them, actually. Because remember our polar form, remember the tables we looked at? A lot of them had just sine and cosine, didn't they? So it's not unreasonable that you would see that fairly often in terms of figuring arc length. And changing something from a rectangular form to this form would allow you to find arc length easier. But again, this is considered an optional topic. I won't put it on test. You like this? You want this on test? It can't be anything hard just from the reason I just said. I mean, like if you look at the problems I have, where are they at? That one might be interesting. That'd be a little bit more challenging. If you're squaring this, that'd give you 1 plus 2 sine theta plus sine squared. The other one would give you cosine squared. Sine squared plus cosine squared gives you 1. And then you got 2 plus 2 sine theta. That looks like one of those trig substitutions. But no, that'd be too much. Like r is equal to 8. Derivative of 8 is 0. So it's like most of them are designed to be super easy. This one would probably be super hard. Okay, let's take a look at a setup on the area of a surface revolution. This is again an optional topic, so I guess I probably figure these are so easy anyway. Then why not? Why make them required? Take a look at 65. R is equal to 6 cosine theta, the interval from 0 to pi over 2, and axis of revolution is the polar axis. In instructions say to find the area of the surface formed by revolving the polar equation over the given interval about the given line. Now, alpha and beta will be given directly, just like we were given. We need f of theta, and again, that's your r. So it's 6 cosine theta. We also need our derivative. So f prime of theta would be, the derivative of cosine is negative sine. So I got negative 6 sine theta. And now we're ready to plug it in. S is equal to 2 pi from alpha to beta, so 0 to pi over 2. We have f of theta, which is 6 cosine theta, and then you have a sine theta here. And then we got f of theta squared. So we got 6 cosine theta squared plus f prime of theta squared. F prime is negative 6 sine theta squared d theta. Now this would give us 36 cosine squared, 36 sine squared. Factor 36 out, comes out of the square root is a 6. So I got 2 pi, and I'll bring this 6 out and the 6 out of the square root. And what happens to cosine squared plus sine squared in the side of the square root? Cancels away. So then you're left with this right here. And then at this point, you can do your u substitution. I won't finish this, but u is equal to sine theta, du would equal cosine theta, d theta. And then you proceed from there. So, but again, I won't put this on the test, but you can see it's not a horrible thing. I think the ones earlier in this section are a little bit more challenging, trying to find those limits of integration. Well, let's go ahead and take a 5-minute break, and then we'll take a look at the next section.